Today, we're looking at what are likely the 4 most famous lines in the Quake 3 Arena source code. The fast inverse square root, a magic algorithm that fundamentally changed how 3D games were rendered at the turn of the millennium. If you weren't aware, Quake 3 Arena is open source, so you can go to GitHub and have a look at all their source code, published by id Software. And in one file, the q_math.c, at line 552, we will find the method q_rsqrt. And this is the famous fast inverse square root algorithm. This method is called millions of times while Quake 3 Arena is rendering its 3D environment. But why is it so important? And where did it come from? And how can we make sense of something that seemingly the developers of Quake 3 Arena didn't fully understand? When id Software open sourced Quake 3 in 2005, the world expected to find genius. But what they found instead looked like a glitch. This single line of code was responsible for the lighting that made Quake 3 a masterpiece. But not many seem to know exactly why it worked or where it came from. So why does this piece of code even exist? Well, in the 1990s, even in the late ones, 3D lighting was extremely hard to compute. And even though we already had 3D accelerators, they were more like triangle factories and couldn't compute complex 3D lighting or physics effects. Those were still computed on the CPU. In order for a 3D engine to determine how light fades over a distance, for instance you have a torch on a wall in a dark corridor, it needs to compute the inverse square root many times. Calculating a square root on a microprocessor from the 90s takes many compute cycles. And if you need to do this thousands of times per frame, well, you can kiss those 60 frames per second goodbye. So developers needed a cheat code, something to bend the laws of mathematics. And this is what the fast inverse square root function is all about. So where did it come from? Well, it's from id Software, so clearly it must be John Carmack, right? No, it's not. The fast inverse square root popped up the first time in 1986. William Kahn wrote an unpublished paper describing how to calculate square roots using bit fiddling techniques, followed by Newton iterations. And we get to this when we are dissecting the algorithm. But the person who is credited with inventing the algorithm is Greg Walsh. At least he came up with a constant that most likely triggered the developer to write this comment. Greg Walsh looked for a way to make the Ardent Titan graphics supercomputer faster. Interestingly, it looks like the algorithm found id Software after taking a detour through 3dfx Interactive. Okay, now we know it exists, we know who came up with it, but why is it there? I already mentioned that if you have to compute the inverse square root thousands of times per frame, your CPU is going to stall. The floating point unit on CPUs in the 90s wasn't as strong, and most of the time, if the FPU was busy, the CPU could not execute other instructions. The idea of the algorithm was to replace floating point arithmetic with multiplication, subtraction, and a bit flip. That would mean that the inverse square root could be computed using the relatively strong integer pipeline. But how does this possibly work? Where it gets really interesting is from line 560 in the Quake 3 Arena math library. This line converts a floating point number into an integer, but not in a conventional way. If you read the comment next to this line, you understand that there is something more to it. And in order to understand what's really going on, we have to understand how floating point numbers are stored in memory. What we want to do is we want to compute the inverse square root of x, and x is set to 4.5. A floating point number is stored in memory as 32 bits. This is based on the IEEE 754 standard. And you can read all about this online. There's plenty of information available. So how is 4.5 stored in memory? First, we have a sign, plus or minus. So the sign bit is the one on the very left. It determines if the number is positive or negative. Now, for our examples, only positive numbers are possible. I'll not get into details, but let's continue now with the next section. 8 bits, and this is the exponent. The exponent is stored in the next 8 bits, and this is 127 biased. So that means whatever value you're setting here in these 8 bits, you're subtracting 127 from it. So in our case, this represents the value 129. and we need to subtract 127 from it, and that gives us 2. So this means we have an exponent of 2. So 2 to the power of 2. And then we have the remaining 23 bits, which represent the fraction or the mantissa. This is basically the last component that is required to store our floating point number in memory. And if we put everything together, we get our sign bit, which is positive, and then we get our fraction or our mantissa. This is basically the 0.125, also implied that we always have a 1 at the beginning. That's why we have 1 plus and the fraction multiplied by 2 to the power of 2, our exponent. And this gives us our 4.5 back. This is simplified to make the numbers easier to read. Now that we know how a floating point number is stored in memory, we can figure out what line 560 is doing. I said before, we're converting a float into an integer. And all it does, it just takes exactly this number and just makes it one 32-bit integer. Exactly what is here. So now you ignore these spaces that separate these three components and just make one large integer. I kept the separation just for understanding, but from now on, we just assume those are integers. And now we can move on to the second line. This is where the magic happens. So we have this one constant, and then we subtract our integer number that we converted from our floating point number, bit shifted by 1 to the right. So this is the binary representation of our magic number. This is exactly this number here. Then we have a subtraction, which is here. And then here is our bit shift. So what does that mean? If we look at our number 4.5, the number that we got here at the top, and compare it with this one here, this is the bit shift 1 to the right. So each number moves 1 to the right. The last one is being cancelled, and we are inserting a 0 to the very left. This is the bit shift by 1 to the right. And then we get this value. This value represents the best possible guess of what the inverse square root of our original value, 4.5, is. The only thing what we have to do now is to convert our integer back into a float. So we are going to split our number again in our three sections. We have the sign, we have the exponent, and we have our fraction. So we have our exponent, our fraction, and then we do exactly basically this what we did here. And if you put this into a calculator, you get 0.467483. And our expected value, this is using pure floating point math. This one here is the absolute correct value, should be 0.471405. So the estimation gives us a very close approximation of the actual value. And you see that the error is less than 1%. That is pretty good. Now I made this 4.5 to make sure that we are using floating point numbers, but let's try 4.0. This looks like an integer, but it is actually also a float. But if you go further down and we have a look now, you see our error is now 3.3%. Yes, the error percentage can deviate quite a lot. This would probably end up in a very flickery experience. And that is why we have one last line in our algorithm. And this is mentioned here, first iteration. This is the Newton method to get from a good guess to a perfect guess. And this is the Newton refinement here. So I'm not going to go into this in depth. You can also look up Newton's method. There is also a lot of information online. So yeah, we'll not go into details how this exactly works. It's again a lot of math and derivatives and blah. So no, we're not going to do this. Just see that there is one more line in the Quake 3 Arena code. It's exactly this one here. And actually there is a second line of the same. Developers noticed that this can be removed. It is no longer needed because it refined our value so well that we only have to do it once. So we have to run our magic guess one time through the Newton's refinement, and then our final output is 0.499, and that is very close to 0.5. And this is what the fast inverse square root is doing in Quake 3 and apparently in other games as well. Okay, then let's start testing. I wrote a small application that is using the fast inverse square root calculation in different versions. We'll look at this in a moment. But let's start with our first 32-bit processor. And this is a 386DX. I clocked it at 33 megahertz because I'm planning on testing a lot more CPUs. I'm not sure how many we can finish today. But yeah, let's just get started. So here is the 386 DX33, it has 128 kilobytes of cache, and we don't have any coprocessor, so no floating point unit in the system right now. Here is my little application. It's the rsqrt.exe. It is compiled using Whatcom. There is a Git repository. It's linked in the video description. If you want to look at the source code or you want to download the executable, you can do that there. But now let's just see what this application does. So the executable is rsqrt, and I can specify two parameters. The first one is how many iterations of calculation should happen and if it's color or grayscale. Let's do 10,000 iterations. So it will calculate the inverse square root 10,000 times. And I want to run it in color mode. Let's run the application. The first test uses the standard math formula. So it is basically a division and a square root. Since I don't have a floating point unit, the CPU needs to deal with that. And it took around 5 seconds. The second test is the fast inverse square root algorithm, exactly how it is in Quake 3 Arena. And this one took 7.2 seconds. So it is slower than the CPU just doing its work. That is interesting. And the last test is exactly like Quake 3 Arena, but without this last line, which is the Newton refinement. So basically just this last line is missing. And this is the fastest. But it had also a higher error than our second test that we're running here in this list. That is a little bit disappointing. I was expecting that the fast inverse square root algorithm is faster, but it isn't, unfortunately. Now, we have these numbers, but there's also something else in this test that I want to try, and this is a graphical representation, how graphics look like with the three different methods. So let's continue and let's draw some circles. Now, this is now extremely slow because we are not having a floating point unit, and I will just speed this up and then we'll look at the circles. Okay, and we're done. So we have 3 circles. The left one is standard math. The center one is exactly the same algorithm as it is in Quake 3 Arena. And the right one is Quake 3 Arena minus Newton refinement. And well, we can see already that the one on the very right is a little bit off. It doesn't blend into the circle on the left. So that is one difference. Also, if you look at the center of the circle, you can see that the one on the right does look different. And I think overall the colors are, well, they don't match exactly what's on the other two. I think the left and the center circle, they're almost identical. Now look at the yellow circle. The yellow top part is longer, is bigger compared to the other two. So this is also a change that I've seen. And overall, if you're looking at how the circles are, for instance, the black one, the pixels look a bit different. So yeah, this is our issue with having a higher error on our bit hack. So without the Newton refinement, this is at least my explanation why it looks like this. I also have a grayscale version. So let's have a look at this one. So we run the test one more time. We should get 5 seconds approximately, 5.4. And the last one was around 4.6. Okay, so here we go. Again, same as before. Let's see what happens to the grayscale version now. And this is, again, extremely slow. So let's just wait until we have our circles. Okay, and here we go. So again, we have 3 circles, left to right, exactly like before. And here we can see exactly what the difference is. So the one on the very right has a black center, whereas the others are white. This is a very easy way to distinguish which method is closer to the original, to the very left one. So the Newton method, even though it's the slowest on this particular CPU, is actually working really well. Now the question is, when did we actually see a performance gain from this method, from the fast inverse square root algorithm? So for the next test, I will add a floating point unit to the system, and let's just see what we get. I'll run exactly the same tests one more time. Okay, now we have a numeric coprocessor present. You see it in the second line, right after main processor 8386DX. Let's run the color version first. Okay. Whoa. Now, because we have a floating point unit instead of 5 seconds, we need 110 milliseconds. So there's a huge difference, and even the Newton refinement got a huge performance boost. That is weird, right? Well, technically no, because there are still some floating point operations in those equations. For instance, the Newton refinement uses floating point multiplication, and there is the conversion from integer to float. But it looks like this CPU in particular cannot really benefit from the fast inverse square root algorithm. I have no other explanation, but this is what I just gave you. If you have more details, please let me know in the comments. If you have some good insights, I will pin your comment under my video. So let's run our color circle mode. Look at this, how fast this was now. So yeah, our FPU makes a huge difference drawing these circles. Okay, last but not least, let's run the grayscale version. Also 10,000 iterations, and it was really fast again, almost the same values, I think, what we got before. Now let's see the grayscale circles. And here they are. And we see exactly the same result what we had before. The center on the very right is black, whereas the others are white. So this is the conclusion for the 386DX. I don't think this will work properly on a 386SX. I haven't tested it. I don't know. Okay. Next test, I think, should be a 486DX266. Okay, and this is my 486DX266. This is a system I built just maybe a few months ago. I made a video about this. The video is linked in the top right corner. Oh yeah, I remember we set up the CD-ROM and everything, proprietary interface. So yeah, very, very interesting. So let's see if we can run it on this system. Nice. So yeah, I think we need a version of the DOS extender. Let's see if we can run our application now. RSQRT. Yes, now it works. 1000 iterations is not enough. So let's just try immediately to go to 100,000. 100,000, and we'll go with a color version. And okay, so we have 384 milliseconds for the standard. Oh, and you see the Quake 3 Arena version now is faster than the standard math. So we got it now down to 330 milliseconds. The fastest is still the one that has our highest error, the one without the Newton refinement. So let's have a look at our color circles. And here they are. This is basically exactly the same what we have seen before. So that's cool, but let's also check the grayscale. And let's run it again. So here's proof again. The benchmark finished in 400 milliseconds for the standard math, 330 for our Quake 3 Arena version, and 219 milliseconds for the version without the Newton refinement. And our grayscale circles also look exactly identical from what we have seen at our 386. Now what I want to try is, I'm not sure if it's possible, I want to try and disable the FPU on the system. So there is an environment variable that we can set, and this is no 87 equals to 1. So let's try this and run the application, but I will not use 100,000, I will use 10,000 because I have no idea what the side effects will be. 10,000, and we use color. Let's see what happens. Oh, you see, we are a lot slower now. Before we had 100,000 operations, now we only had 10,000. So yeah, if I would have done 100,000, this would have been a lot longer. But we can see again that the Quake 3 Arena version is slower than standard math. This is something that we have seen on the 386 as well. Very interesting to see. And now with no floating point unit, we can see that also our circles are drawn a lot slower. But the output will be exactly the same. And here we are, all the circles are drawn, and we see again the same output from before. So yeah, that's pretty awesome. So we could disable our floating point unit using this one environment variable. I believe this only works with applications that are built or compiled how I compiled it. By the way, the instructions are also on the GitHub page how to compile this. I hope you enjoyed this video digging deeper into the fast inverse square root calculation that is used in Quake 3 Arena and apparently in other games as well. We have seen that from a 386 to a 486, this algorithm actually is faster. It wasn't on the 386, but on the 486 it is. Now the question is, what is going to happen on a Pentium system? Now, because this is already a very long video, I want to stop it here. But I want to know from you, which CPUs do you want to see? I have a few interesting ones that I want to try. For instance, we have Pentium MMX. We have K6 CPUs, K6-2 and K6-3. But then also we have the slot 1, Pentium 2. We have the Pentium 3. And also maybe a slot A, an AMD Athlon. Let me know in the comments which CPUs you want to see. Then we'll make another video just benchmarking different CPUs. And maybe these benchmarks also give you an idea which CPUs are better utilized in Quake 3 Arena because of the fast inverse square root algorithm. Okay, and this is all I have for you today. You know, if you want to support this channel, please head over to Patreon or become a member directly here on YouTube. Thank you so much for your time, and thank you to all of you who are already supporting this channel. I hope you're looking forward to the next videos. Take care and bye-bye.